at IAGE, working in the group of Professor de Gouveia Pino. And today I'm going to talk about my continuing work on studying the growth and feedback from central black holes in galaxies. And I will focus on both supermassive and intermediate mass black holes. And some of this work were done by collaboration with my previous collaborators when I was a postdoc at SNS PISA. So we have heard several times this conference that the feedback from central black holes in galaxies is a very important component in galaxy formation. And this is routinely incorporated in models and in numerical simulations, because without it, the more massive galaxies produce a lot of stars, and star formation is too high as compared to observations. So AGN feedback acts to quench this star formation. And in this way, it reduces the number of massive galaxies, and it brings the, for example, the dark matter halo mass function consistent with the observed stellar mass function at the high mass end. And in the lower mass end is supposed to be more, supernova feedback is supposed to be more important. Now I should mention that this whole scenario is called the negative feedback, or where the star formation is quenched or reduced by the feedback. There can be also positive feedback by AGN, where star formation is induced by the compression of clouds in an inhomogeneous medium by these AGN feedback. Now, these are sometimes observed, have started to being observed and being simulated in numerical simulations. Now, my talk will focus on this negative form of feedback where the star formation is quenched. Now, I will skip the introduction that the system that we simulated was a high redshift quasar as we see them greater than 12.5 giga-year ago. So the quasar SDSS J1148 at redshift 6.4, this has a central black hole of 3 times 10 to the power 9 solar masses, and it is observed to host a large-scale outflow, which is manifested by this carbon-2 emission line with a broad feature. So this broad line, it traces the outflow, and the mass outflow rate of around few thousand solar masses per year. Now, we tried to simulate this kind of a system in a cosmological hydro simulation. Now, introducing the work of intermediate mass black holes, black holes are mostly observed to be either stellar mass, or which means less than 100 solar masses, or supermassive, which is greater than 10 to the power 6 solar masses. And these supermassive black holes are observed as AGN at the centers of galaxies. Now, naively thinking, there should be a population of intermediate mass black holes in the middle mass range between 100 and 10 to the power 6 solar masses. And they have started to being observed at the centers of galaxies, especially at the centers of dwarf galaxies. And these should also have feedback similar to the supermassive black holes in AGN. A very exciting idea was proposed by, in this paper by Silk, that essentially all dwarf galaxies in the high redshift universe host massive black holes. And feedback from these black holes, they affect the dwarf galaxies between redshifts 5 and 8. And it quenches star formation in these galaxies. And it, in the same way as AGN does, it reduces the number of dwarf galaxies in like this intermediate mass range. And these physical processes can potentially solve several problems that are faced by numerical simulators who study dwarf galaxy populations. For example, there is a core cusp problem, and the numerical simulations tend to overproduce the number of dwarf galaxies. And this kind of feedback can try to solve these problems within the lambda CDM cosmology. So we performed cosmological hydrodynamical simulations to study this scenario of intermediate mass black hole feedback at the centers of dwarf galaxies. Now, I have one slide on introducing the idea of cosmological hydrodynamic simulations. So here, the computational box, it represents a volume of the universe, and the resolution elements in the box represents matter. The initial conditions are at the epoch of the cosmic microwave background. So now we start with the primordial density fluctuations, which are Gaussian, and then using the laws of physics, we try to see if the final structures that we get at later redshifts are consistent with what are observed. So in this nonlinear evolution, the two main forces which are acting are gravity, which affects both dark matter and baryons, and hydrodynamics, which affects only baryons. And in this whole scenario, we use the lambda CDM cosmological parameters, which are taken from the most recent observations by Planck. And I have been using a modified version of the gadget code to do these simulations, which tracks gravity using a TreePM method, and hydrodynamics using the SPH, smooth particle hydrodynamics. And it was originally written by Volker Springel, but then all the other sub-resolution physics were included by several people throughout the world. For example, metal line cooling and heating are taken from this paper by Wiersma 2009. Then there are models for star formation, stellar and chemical evolution with contribution of these 9 metals and production of the metals from supernova and evolved stars. And of course, there is supernova feedback and accretion of gas onto central black hole and feedback from them. And personally, I have worked on the supernova feedback and the AGN accretion and feedback part in my previous papers in collaboration with my Italian collaborators. So here is showing the gas density evolution in a 2 megaparsec cube cosmological volume, starting from a redshift 8 and going up to lower redshifts. Here we can see that initially the gas is more uniformly distributed, and as time goes on, they collapse and form these kind of filaments, and the intersection of the filaments correspond to the galaxies, and the location of the black holes, as I will show after some time. So how do we include black holes in this simulation? So we generate seed black holes at the centers of galaxies depending on certain mass threshold. So in my supermassive black hole work, I seeded black holes of 10 to the power 5 solar masses when the halos reached 10 to the power 9 solar masses. Because here we are studying the more massive galaxies. Whereas in the intermediate mass black hole work, I scaled down both of these numbers and generated seed black holes in smaller galaxies. And then these black holes grow by the accretion of gas around them and by merger with other black holes. And as they grow and accrete, they have a feedback which is implemented by a transfer of energy from the black hole to the surroundings. I think I'll go a bit fast here. I can explain later if there are some questions. So we assume a Bondi-Hoyle-Littleton accretion rate and limited to the Eddington rate. And a fraction of the energy is radiated away, and then a fraction of that is coupled to the surroundings as feedback energy. The equation, so how the feedback is implemented in the simulation is given here. So we assume an energy-driven wind where the feedback energy is equated to the kinetic energy of the wind. And using this and the previous equation, we can write the mass outflow rate in terms of the black hole accretion rate. And this accretion rate is computed using the Bondi accretion equation I showed before. And from there, the outflow rate is computed. And then we use a probabilistic method to distribute the energy by giving a velocity kick or momentum to the gas around the black hole. So the center is the location of the black hole, and we distribute the energy in a biconical volume like this. So in the supermassive black hole work, we performed zoom-in cosmological hydrodynamic simulations. And I am not going into the detail of the techniques, but I can describe it later because I have to, it will take some time. So the total size of the box that we simulated is 500 megaparsec, because here we want to resolve a very high redshift massive quasar host galaxy. And then a region of, so there is a dark matter only simulation, and a region of it is zoomed in with the gas or the baryons. And that zoomed in region corresponds to 5 megaparsec. And so the halo that we zoomed in was a mass of 4 times 10 to the power 12 solar masses at redshift 6. And we performed several simulations, one with only star formation and supernova feedback with no black hole or no AGN in this case, and few by varying the sum of the parameters of the AGN feedback model. Now, similarly, in my intermediate mass black hole work, we performed one run. Okay, I should mention that these are not zoomed in, but these are fully cosmological hydrodynamic simulation, or we are evolving a periodic cosmological volume with these periodic boundary condition, which is like a representative volume of the universe. And the volume is a 2 megaparsec cube, and starting from redshift 100 and going up to redshift 4. And regarding the physics of the black hole versus supernova, there is one run with supernova only and several other runs by varying the parameters of the AGN feedback models. So here I'm showing the formation of structure and the growth of the black holes together. This is a 2 megaparsec cube volume, and this is actually my supermassive black hole work, like going up to redshift 6. And in blue, showing the gas density, and the red circles here correspond to the black hole masses, but of course they are not according to scale, because here, well, the sizes of the black holes are much more exaggerated here. It is just to show that as gas infalls towards the center of the halo, the black holes are also accreting some of that gas, and they grow, and at the same time, it also has feedback. This is a still picture showing the growth of structures starting from redshift 10, 9, 8, 7, 6.5, and 6. Okay, here plotting the growth of the black holes at the galaxy centers. So this plot showing the growth of the intermediate mass black hole in the fully cosmological hydro simulations. And for each of the curves correspond to one of our simulation. And the most massive black hole in that run. So we see that starting from 100 or 1,000 solar masses at around redshift 20, we can grow to 10 to the power 5 or 10 to the power 6 solar masses by redshift 5, except one of the cases. And similarly, in the supermassive black hole case as well, because here we are, okay, so I should mention that the intermediate mass black hole, this was for dwarf galaxies, and this is for the high redshift quasar. So we see that using the same methodology, we can grow the black hole very similarly in either dwarf galaxies or in a high redshift quasar. And this is the impact on star formation, showing the star formation rate density in solar masses per year per megaparsec cube as a function of redshift. Now here, the blue curve in the background is this one. This is a supernova only case where there is no black hole feedback. And all the other curves include black holes, accretion, and feedback. And we see that there is this reduction in the star formation in the other runs as compared to the supernova only run, which is at the back here. And this shows that as the black holes are growing, they are quenching star formation. This can be visualized in a, if we see the black hole growth and the star formation rate figured together. So these are the cases. The colors are the same, remain the same. And if we consider the cyan curve, the black hole grows up to 10 to the power 4 solar masses here only. And the star formation, we can see that there is not an impact as compared to the supernova run. And only the black hole which grows above 10 to the power 4 here or above 10 to the power 5 has this impact on the star formation. For example, this red curve, here the black hole grows the fastest, and that is why it has a earlier quenching of star formation. a very similar outcome is I also find in the supermassive black hole work. So when the black holes have grown to more massive, then there is a quenching of star formation as compared to the case where there is no black holes. So this provides the evidence that the growth of the black holes are quenching star formation. And here showing the black hole accretion rate in plotting the Eddington ratio, which is the black hole accretion rate divided by the Eddington rate as a function of redshift. So for both of the intermediate mass black hole and the supermassive cases, I find that the black holes start growing quite a very low Eddington ratio, and they grow gradually. Now, to form the supermassive black holes, I find that they need to accrete at the Eddington rate for few hundred mega year, but these intermediate mass black holes have not reached the Eddington rate yet by redshift 5. So here is a movie showing supernova and star formation only case in the top and the case with black hole in the bottom. And it shows the density in the left panel and temperature in the right panel. And I will just play it again. So we see that the case with AGN has these very hot outflow structures which correspond to the feedback from the central black hole, creating these outflow which gets shocked and is these hot structures. And you can see that this corresponds to the low density structure here. And they are kind of pushed by the AGN outflows. Okay, this is the figure showing just the previous movie. And just quantifying in terms of the radial profile of gas density and the star formation rate, we find that at redshift 6, AGN feedback can reduce the central density of galaxies by 100 times. And the star formation rate surface density can be reduced by more than 1,000 times. And here showing the gas density and temperature, a similar kind of plot as above, but this is for the intermediate mass black hole case. And here we do not see very strong outflow signatures, which were shown in the supermassive black hole case. Only we find some kind of shocks here for the most massive black hole. And this is my last figure. If we plot the central black hole mass versus the stellar mass of these galaxies, we find that they lie above the relation. Okay, the black line here is the redshift 6 M black hole M stellar relation, and the dotted line is the redshift 0, and taken from observations. And observations already find that the redshift 6 relation is higher than the redshift 0 relation, and we find that at higher redshifts, the black hole lie even higher than there. And this is the case comparing the supermassive black hole range that in the lower mass end, they follow the redshift 0 relation, but okay, this has to be consistent because we simulated that system here. So to conclude, we find that starting from 10 to the power 5 solar mass seeds, we can grow the black hole to supermassive or 10 to the power 9 solar masses in a cosmological environment. And this needs Eddington accretion, so the black holes need to grow at the Eddington rate for hundreds of mega year. And these results are published in this paper. And we find that the most massive black holes, they generate powerful outflows, and the outflow mass is increased and the inflow is reduced by up to 20%. And in the intermediate mass black hole case, the study is Barai and Gouveia Pino is a submitted paper and is on the archive. And there we see that using a very similar approach, we can we can shift the whole range to lower masses, and we can grow these intermediate mass black holes at the centers of dwarf galaxies. And here, the maximum Eddington accretion ratio is around 0.9. And star formation is quenched when the black holes have grown to a few times 10 to the power 5 solar masses. So this shows that these intermediate mass black holes at the centers of dwarf galaxies can also be an important source of feedback. And if this scenario is correct, then this feedback already turns these galaxies passive or quenches star formation at high redshift, and the black holes are turned dormant because there is no gas which has already been pushed out. And this could be a reason that it is very difficult to observe these black holes at the centers of dwarf galaxies. Okay, thank you.